Hello there, welcome back. This is lesson 6 in our unit 3B, and today's lesson is called molecular polarity. So in the last video, we talked about bond polarity, and how to determine if you have a polar or non-polar covalent bond, and we talked about bend or the bond electronegativity difference, and based on that, we were able to determine the type of bond we had. Now, today we're going to talk about molecular polarity and something called SNAP. So first thing I want to mention is a dipole. So we mentioned this in the previous video. And so a dipole exists when you have an unequal sharing of electrons. So unequal sharing of electrons, that is your polar covalent bond. Now, a dipole, it means to have two opposite charges. So one side has a kind of partially positive side, one side has a kind of partially negative side. So if we look at, water, and if we make this diagram even better by adding our lone pair electrons, now we know electrons are being shared in these bonds. So we can't have full charges. If you have a complete positive or complete negative charge, that means the electrons were transferred. That is an ionic bond. But here, oxygen has more control over the electrons. Hydrogen does not. So this is why drawing the lone pair of electrons are important. We can literally see the extra electrons around oxygen, and so we give it a delta negative. So this is delta negative. And what that means is that it is partially negative. Because remember, electrons are negative, so the more electrons oxygen has around it, the more partially negative it is. Oxygen is also the more electronegative atom in the pair. So that's how you're able to determine that. And then if you're drawing your dipole arrows, you always draw them pointing to the negative. So if we know oxygen is going to be delta negative rather, because of the extra electrons, that means hydrogen has to be delta positive. So one is the opposite of the other, and you're always pointing your arrow to the negative end. So if we're going to draw them, if we draw our dot diagram for HCl, now I'm just going to draw the final product of the dot diagram. If you need to, have all those steps, go back to those videos. But here's HCl. And we can see that chlorine has so many more electrons around it. So chlorine will be delta negative, and hydrogen will be delta positive. So the more electronegative atom in the bond will be the delta negative. So this is more electronegative, and it has those electrons. So again, your arrows, we're just going to point them to the negative side. And that's it. So the way they have a little line at the end and they point to the negative, that is how you would draw that. If we draw CO2, so remember CO2 looks like this. This was one of the super important ones that you need to know how to draw. So you have it like this. Whenever you draw a dipole, you want to look at each individual bond. So we have this C and this O. And so O is going to be delta negative. C is going to be delta positive. Again, O has those extra electrons. And so in that green pair, we have an arrow pointing towards O, the more negative side. And then if we look at, in the blue box, the C and the other O, C is delta positive still, O is delta negative, and now you have that dipole. So here you have two dipoles. So again, you want to draw a dipole for every pair that you have. Okay. Another important shape that you need to know how to draw is water. Oops. Completely messed that up. Okay, there is your water molecule. And again, if we're going to look at individual pieces, we have this H and this O. So O is going to be our delta negative, H is going to be our delta positive, and our dipole is going to point towards the negative. And then if we have the green one, O is still going to be delta negative, H is delta positive, and so it goes up towards that O. Okay, and one last one, because we're going to revisit these compounds later on, is CCl4, which looks like this. Remember, all of these lone pair electrons are important. Oops, that looks weird. Okay. So now we have 4 different bonds here. We have to assign 4 different dipoles. So let's look at this one first. Cl and C. So of this pair, chlorine will be that delta negative, carbon will be that delta positive. This arrow will go towards Cl. In the next pair, carbon is still delta positive, chlorine is delta negative. This dipole will go that way. And remember, you're always pointing towards the negative. In this pair, with this C and this Cl, carbon is still delta positive, chlorine is delta negative, so the arrow goes that way. And then lastly, we have this Cl and this C. Again, chlorine will be delta negative, and you have a dipole going that way. So I know it's getting kind of hard to see, but we had one going up, we had one going this way, one going this way, and one going that way. Okay, so now knowing how to draw dipoles, we can tell if a molecule is polar or nonpolar, and that's where SNAP comes into play. So just like BEND, which was a acronym for bond electronegativity difference, SNAP stands for symmetrical nonpolar, asymmetrical polar. So up until now, we've been talking about how bonds can be polar or nonpolar, but molecules can be nonpolar or polar as well. And so we use this acronym right here. So if a molecule is symmetrical, then the overall compound molecule is nonpolar. But if the molecule is asymmetrical, it is polar. So again, we're going to go over what that means and how to figure that out. Basically, if a molecule is asymmetric, there is a net dipole. And what that means is that one side of the compound has a stronger pull for the electrons. So if we look at symmetrical molecules, for example, if we were to cut this compound in half, no matter which way we cut it, we will always have the same piece. So if we cut it like this, both sides are the same. If we cut it like this, both sides are the same. If we cut it like this, both sides are the same. If we cut it like that, both sides are the same. So that's one way to kind of look at it. Another way to look at it is, well, your dipoles cancel out. So this is one we did before. So you have one going up and one going down. So they cancel each other out. You have one going right and one going left. They cancel each other out. And so that would be your symmetrical molecule. And one thing that's super important, symmetrical molecules have an even distribution of charge. So if you look at this, one part of the molecule isn't really stronger than the other. One side's not stronger. Everything's kind of evenly distributed. So if we look at asymmetrical, it's a little bit different. Now, if you fold or cut the molecule in half, and even if you can fold it in half a million times and get the same thing. If one time you get something that and both halves are different, it is asymmetrical. And so we're going to demonstrate that. Yes, if you cut water in half like this, you get the same thing. But if you cut water in half this way, you don't get the same thing. You have O on one side, H on the other. So using that method, that's asymmetrical. Now, if you go to draw the dipoles for this, remember they point negative, they point towards the negative. So here, they're both pointing in the same direction. So they don't cancel out. It's like two people pushing something in the same direction. Oxygen clearly has a stronger pull for the electrons. And so there is an uneven distribution of charge. All these electrons are not shared throughout the molecule evenly. And so when we're trying to figure out the polarity of a molecule, again, we have to draw the dot structure. We have to determine the polarity of each bond, add the dipoles, and then see if they cancel. So basically, you need to bend and snap. So looking at it in the bend and snap frame, again, bend, you're finding the electronegativity difference for each bond. You have to look at the bonds first. Then, once all the bonds are looked at, then you look at the molecule itself and snap. So if you are a Legally Blonde fan, or if you've never heard of this at all, you need to go watch this. When we're talking about molecular polarity, we bend and snap. You just do it. Okay. So an important thing to note here, and I'll show you an example, is that you can have a non-polar molecule. Oops, my bad. A non-polar molecule with polar bonds. So that's why we have to look at each part first. Okay. So here we're either going to look at the same compound we were looking at before. And here we have HCl. So we have, if you were to calculate the electronegativity difference, we would have 0 nonpolar bonds and 1 polar bond. HCl is a polar bond, and you can even see that by the electrons. So that means H is going to be delta positive, Cl is going to be delta negative, and we draw our arrow. So that is bend. Bend in green. We looked at each individual bond, there's only one bond, assigned the dipoles. Now we have to snap. And so if we look at the symmetry, if we cut HCl, we get different pieces. If you cut in half like this, you get different pieces. Also, there's only one arrow. There's nothing to cancel it out. This is going to be asymmetric and polar. So the molecule itself is polar. So we have polar bonds, a polar molecule, and we have uneven charge distribution. And so that's it. Next is we're going to revisit CO2. And a lot of this just comes with practice. Grasping this at first is kind of hard, but it will make more sense as we go. So first we got to bend. So we look at this bond. This is positive, this is negative, that arrow. And then we have to look at the other one. So you have to look at each bond first. Carbon still positive, oops. And so oxygen is going to be that delta negative. Again, they have to be opposites. Arrows go that way. So we have 0 nonpolar bonds, and we have 2 polar bonds. So a good rule of thumb, if you have extra electrons drawn, good chances that is a polar bond. So is this molecule polar, yes or no? Now we have to look at SNAP. Is our compound symmetrical? So the answer is it is. If you cut it this way, if you cut it that way, this way, that way, you always get the same thing. And you can also look at the dipoles themselves. One's going left, one's going right, so they cancel each other out. So this is not a polar molecule. So this is what I meant before. You can have polar bonds, but have a non-polar molecule. And here we have a even distribution of charge. So remember, polar molecules have uneven distribution of charges, non-polar molecules have even distribution of charges. Okay, H2O, let's look at this one again. It looks like this. And again, we drew our dipoles like this. And then we do the other one like that. Okay, so that was our bend. We did that in both colors. Now we have 0 nonpolar bonds. We have 2 polar bonds. Again, you can calculate those electronegativity differences should you want, but seeing those extra electrons is kind of a dead giveaway. And now we have to snap. So first, if we look at the dipoles, we have one pointing right and one pointing up, but we can kind of see there's an overall pull of electrons in that direction. So this part, this side, is stronger. So right off the bat, you should give it, okay, cool, that's asymmetrical. Also, if you were to cut this in half, let's say like this, or like that, that's also asymmetrical. So this molecule is polar. And again, that is an uneven charge distribution. Again, the readings only ask you about a handful of compounds. So we're going to continue practicing this and just focusing in on the important ones. Okay, almost done here. Let's revisit this one. So CCl4. Okay, so if we're going to look at our dipoles, this one's delta negative, it goes up like that. This one, actually, let me just draw the dipoles because this one will get a little messy. Okay, so as I'm drawing this, what do you think, what's your prediction on the type of bond and the polarity of the molecule? So the bond polarities and the molecular polarities. What's your guess, your prediction? Okay, so let's see if your prediction is correct. Remember, this one's going up, this one's going that way, this one's going this way, and this one is going that way. Okay, so this was our bend. If you want to know how these dipoles were drawn, go back to the start. This one just gets a little bit messy. Okay, so again, we have 0 nonpolar bonds. We have 4 polar bonds. And now we have to snap. So look at the symmetry. So if we cut it this way, this way, this way, that way, it is always going to be the same. But if that doesn't really work for you, look at the dipoles. We have one going down and one going up. So that shows you that those two cancel out. You have one going left and one going right. Oops. One going right, one going left. They cancel each other out. So if you have oppositely pointing dipoles, they cancel out. So this molecule is nonpolar, and we have an even distribution of charge. Okay, so I know this was a long one, but there is a bunch of examples that we walked through. So again, you can rewatch this as many times as you want until it makes sense. We are going to continue practicing this in class, but the next video in a couple of days will cover intermolecular forces, and so there are a few that we're going to talk about. They're all listed there. But on that note, have a wonderful day.